Wow, I'm really, thanks for all showing up early for Dan's talk. Really appreciate that. It's hard to get a good spot. You got to get in an hour early. This is the German way to punish people for being late. So I just want to say thank you to all of the people that were at the camp in 2007, because basically this entire project came together because I was pretty tired and listening to Torbjørn Petersen, who's this amazing forensics guy. Is he here by any chance? Are you here? You're great. So basically he made some like offhanded comment in his talk about like the golden way to do memory forensics and the desire to like have a way to get a whole system memory image, and we were talking briefly about maybe we could attack encrypted swap and like maybe there was a way to do that because people use encrypted swap a lot. And so I had some like thought in my head that maybe we could look at remnants of memory, because he mentioned some memory stamping research that someone had done, just like some small footnote on his slides. And I noticed that when I powered off my ThinkPad that there was like a considerable amount of data in memory, which was sort of, I mean, it's not surprising if you've read any of Peter Gutmann's talks about memory retention and different memory types, but I was really surprised that it lasted for say 10 or 20 seconds in the middle of a warm, rainy Berlin summer. And so Seth Schoen and I immediately started working on weaponizing this because we thought it would be really useful. Well, weaponizing maybe isn't the politically correct term, but I'm not a CISP, so. So basically, we started working on like this small assembler program to dump memory, and that was a big waste of time. And instead, we decided to talk to a really serious embedded engineer, Bill Paul, and while drinking soda pop at a party at my house in San Francisco, he came up with some designs and like, I don't know, 20 minutes later wrote the first memory scraper and weaponized it so that it worked via PXE. And so I'm going to talk a little bit about this. Anyway, so this is our team. You will notice that it's missing one person, which is Rick Astley. He's not up there, but when we won the Pony Award, we both won a Pony Award and Usenix Security Best Student Paper Award for this. We didn't include him, but the Pony Awards did, and I won't rickroll you now. But basically, the way that our team came together was that while working on this at the EFF, a number of people came to know about the attack, and each one made some suggestions, and it was kind of like bike shedding. Like, how many different intellectual contributions can we add to this paper? And at some point, Nadia Hettinger became involved, and she's a complexity theorist at Princeton, and she came up with some novel ways of recovering keys that are in memory. And she's actually greatly improved on these, and so when I get to those, I'll actually tell you the new figures, because this is talking about the paper that we published, and that's in the proceedings. But it's not the most current thing. So you can go to that webpage and you can download the source code, videos of the talk that we originally released, as well as some images that explain decay, which you can see on the first slide, which is basically a bitmap spread out in memory and how it decays from one point in time to another point in time. So my slides here are kind of skipping around. So. I mean, basically, who here, before you heard about this, thought that maybe when you turned your computer off, you were, like, safe? Anybody? Wow, I love you guys. You're the best. You're all smarter than I am by orders of magnitude. Essentially, a lot of people that I talked with about this really felt like memory was something that when you powered a machine off, you were, like, pretty much good to go. Like, maybe there was, like, a millisecond or something like this. And in that millisecond, obviously, if you could power on the memory, then you would be able to retain the state that's in the memory. And the US military and other militaries around the world have known about this for a long time. They make a lot of their hardware very tamper-proof. And I heard a rumor that in the mid-90s they used liquid helium to extract secrets from people's memory. And I thought about this, and I was trying to think of some ways to improve on that after hearing this rumor. I'd never seen any papers that explained like this in modern computers. So we went through and we read a bunch of different papers that sort of talked about this in older memory types, and Goodman kept coming up again and again because he sort of is the godfather of most security things on the internet, I think, is a kind of a fair thing to say. And Skor-Borgetov also wrote an interesting paper that basically talks a lot about ways that we can make more efficient memory chips. And one of the ways that you can do this is by cooling the memory chip. So it's like there's an obvious relationship between cooling memory and retaining the state. And then there's a guy by the name of Tal Garfinkel who also noted that this was possible. And boy, I sure wish I had read the prior literature before going through all this work in the first place. But he basically said that it was a really good idea that you should securely deallocate things. So when you like free memory pages, you basically just leave it lying around in memory and hope that no one ever goes around to look at it. So if someone roots your box and you've recently shut down Apache, it doesn't mean your keys aren't in memory anymore. Your keys could very well still be in memory. It just is a sort of it's a different game to try to recover it. But reading out the raw memory, even without powering the machine off, obviously will lead to these things. So they wrote this paper and they created a secure deallocation routine so that it implemented zero pooling. So when you zeroed something, it added it to a pool, and then it would sort of, when the machine was idle, it would look at all the pages that were marked in a particular way, and it would zero those out. So the idea was to not introduce like huge performance loss, but also to add a bit of security. Because like, for example, when you look at, I think it's Thunderbird, if you open the password manager in Thunderbird or Firefox, you'll see all these passwords in memory, and obviously since they wrote it in C, they can securely deallocate it, but they don't. So when you close this application, it like leaks all this stuff in memory, which is not like that big of a deal, except that when you put this together with being able to remotely exploit it over the network, it starts to be kind of a problem. So we looked at a whole bunch of things, and basically, like I said, ThinkPads were like the golden goose. Like just like every ThinkPad we tried had like the best memory retention times. We found one ThinkPad, it was like a T24 or something like this, and it had like I think 30 seconds without cooling. Like you could turn it off and count to 30, and if you got to 31, maybe you had noise, maybe you still had data, which was like kind of a freak occurrence. But let's see. So one of the funny things is how we also found, I guess, some bugs, right? Because there are some bugs in software. Basically, in macOS 10, we thought that maybe it might have some bugs because we'd heard rumors that there were bugs in macOS 10. And the Apple security team was very nice about this, by the way. They said that they were going to fix it someday. We found a bug in macOS 10 that was hilarious. I mailed BugTrack about it, and well, that was a big waste of time. But someone did reply and said that they had found this bug previously, which was that loginwindow.apps actually stores your login and password in clear text in memory forever, as long as you're logged in, even when you lock the screensaver. And Apple Security told me in a confidential email that it was because they needed to use that to escalate their privileges when they needed to escalate privileges without bothering the user, which I thought was like, kind of the point of like prompting the user for things. But hey, so there's some sort of like, I don't know, RPC privilege escalation in macOS 10 that, well, you probably know about other ones, but basically they kept it around. And so they also do some really strange things where if you just like pull the battery out of the machine, it's often they ship in hibernate mode that writes out the state of memory to the disk so that when you put the battery back in, it restores all of this data. So like if you wanted to try to somehow extract the memory but you failed, you could put the battery back in and turn the machine back on and it would restore the memory image. And then even if it was encrypted, it automatically decrypted it and loaded it into memory for you, and then you could try again. Which I thought was like totally great. So we wrote some tools, like I said. We have a couple different exploits which you can improve on by taking out all the calls to printf if you want, because they're unnecessary. You don't really need to know what it's doing. I mean, it's either successful or it's not, I guess. So the USB stick is kind of cool because Bill, he didn't want to buy another USB stick. So he had some iPod that was like the first generation mini iPod, and he repartitioned it and put the firmware in a different partition, and then set up a boot record and made it so his like disk dumper worked, so that you could like see that the iPod was a normal iPod, and you could like play music on the iPod, but you could also boot off the iPod, dump all the memory to another raw partition, and then like not corrupt your MP3s that you had legally purchased from the Apple iTunes store. And and I thought that was really hilarious. Like some people would just like go to the store because it would make it a lot easier, and he's like, you know, the hacker's hacker. So he wrote your Ethernet driver in FreeBSD. Certainly. So he and I sat down and basically talked about like some different ways that we could weaponize this, and we were thinking that if there were machines that met a certain set of criteria and you could control them when they booted, like who here runs like a server farm, maybe that re-images itself occasionally when you want to re-image a machine? Anybody? Okay, so if you run it on crap hardware without ECC memory, you might be in trouble for a number of reasons, one of which is because basically when you reboot the machine, say to update it, and say you PXE boot it, there isn't really a way to do like a trust chain. So you can't really know which image you're booting on that machine. I mean, maybe with Core Boot you could hack something together and make it possible, but basically out of the box you just kind of trust the first thing that hands you something to boot. And when you do that, you're essentially going to end up in a state where you will basically be able to read out all of the memory from the previous boot, especially if you've just done a simple reboot because you had, say, hit the remote console server and just like, you know, flip the power for a second, or if you have done a soft reboot from software itself, like using some sort of administrative console. So in doing this type of boot, you will end up in one of the very few states where you can remotely over the network read out the memory, which is like, whoops, up on that one. So if you do that, you should stop. And we also made we also made another network boot app, which was not PXE, but it's rather the macOS 10 EFI bootloader stuff. And it's so funny because the PXE bootloader is great. Like you can just spit raw frames out onto the network. So let's say you're an attacker on someone's network and you get them to load your small program. Your program is under 10K, so you could really, if you wanted to, you could make it as big as you wanted. And so that it looks something about the normal size of whatever normally goes across their TFTP network. And so basically, we also made one that was a little bit bigger. The EFI one was like, I don't know, 380K or something like that. It was significantly bigger because we had to write our own TCP stack, or rather we ported the BSD one to it. And so basically, between those two, we could attack almost all of the EFI machines that run with Mac hardware, and basically every PC that ships. There are very few like other machines that were really interesting to us, but you could really easily change the EFI code so that it worked with normal Intel machines that are not made by Apple. It wouldn't be too difficult. But the great thing about the network attack is that you can dump the memory network to the broadcast address if you wanted to. And then you can sniff with a different machine and reconstruct it, and it would be really difficult to well, you know, find the machine that had been doing this. So like depending on the way that the network architecture is set up, that could be, I don't know, maybe kind of bad, a little bit, potentially. And you know, this is there is a story to go with these tools, which is kind of sad, which is that unfortunately when you write tools like this, as some people know, total assholes use them. And that's like, you know, what happens when you write software, right? But I got an email from I might actually have the email, I could probably bring it up. But I got an email from an intern at the Department of Homeland Security. Hi guys. They were saying like that they had you know, caught a guy who was like potentially, you know, a criminal, but they hadn't like been able to pin anything on him. And if they could just like recover his memory and extract the keys from memory, then they could like break his